Good afternoon everyone. So today we will study the conventional AC and DC traction drives. Okay. So we get power. Locomotives get power through the transmission line, overhead transmission line, that is 25 kV 50 hertz line in India, and by using pantograph. Okay. So and it is connected to the primary of the transformer. Okay, it is housed in the locomotive. Okay, and then it is given to this. So this is the case. So this is our 225 kV 50 hertz line. Okay, so this is high voltage line, and through pantograph it is provided to the locomotive, and this is the primary of the transformer. Okay. So basically it is a step down transformer. So given to the primary of the transformer. Okay, so this is primary of the transformer, and it is step down. So this is high voltage is step down, and this is secondary. Okay. Secondary of the transformer. So we are so step down, and it is rectified to this rectifier, and this rectifier DC is supplied to the motors. It can be DC or AC. So if there is AC motor is there, so we connect high inverter which convert this DC into AC. Okay. So let us discuss the first traction drive. This is 25 kV 50 hertz AC traction using on-load transformer gas change. So first we will start with first drive. It is 25 kV 50 hertz AC traction drive using on-load transformer tap changer. Okay, so this is 25 kV AC traction locomotive, and this is on-load tap changer. On-load tap changer. So we obtain power from this overhead line, okay, which is running on the above of the railway tracks, and ground is provided by using one of the wheel of the train. Okay, so this is 25 kV line, and it is getting power through this pantograph, and it is receiving power by this primary of the transformer which is kept in locomotive, and then the voltage is stepped down. So this high voltage is stepped down this using this step down transformer, and here we use this bridge rectifier, uncontrolled bridge rectifier. Okay, so which convert this AC voltage into DC, and we use inductor LD which work as a filter. So it filter out this DC voltage, okay, and it is given to this traction motors. Okay, so these are 4 traction motors. So here we are using DC series motor. So this is the power circuit. So it is 25 kV line, transmission line. It is pantograph. It is primary of the transformer, secondary, and the secondary of the transformer has got so many tappings. Okay, so the tappings can be 20 to 40 taps on the second. Okay, so by changing this tap, you can change the voltage across the armature of this combination of DC motors. Okay, so we start from 0 voltage. Okay, and then we goes on increasing this, changing this tap. Okay, so voltage will change accordingly to the given taps. Okay, so if you tap is here, so voltage will be 0. So to increase the voltage, we change this tap from this. So this is 1, this is 2. So first tab 2, second tab, then third, then fourth, fifth, and so on. Okay. So in this way, we can change the tap change, the voltage. Okay. So voltage applied to this rectifier will be changed. So according to the output will be changed. So this will be VA. Okay. So this is the voltage input to this armature. Okay. And by changing this armature voltage, we can control the speed of these DC motors. Okay, so we can change its speed, torque, and so we can go with start from 0 voltage. Okay, and achieve higher and higher speed. Okay. So this type of arrangement is used in both mainline and suburban trains. Okay, so mainline and suburban. Okay, mainly it is used in mainline. Okay, mainline. So the starting of this motor and speed control and torque control can be done by changing these taps. Okay, so by changing this tap, you can control the starting of the motor, the speed control of the motor, and torque. If I changing this, so this AC 225 kV high voltage is stepped down using this step down transformer, and the voltage can be varied in the secondary side by using these taps. Okay, and let's suppose this is at 0%, is 10%, 20, 50, 60, and 100%. So you get the voltage correspondingly. Okay, and this voltage is fed to this bridge rectifier, and it is a DC motor. Okay, so it needs DC voltage. So this AC voltage is rectified by using this bridge rectifier, and inductor is connected. DC link inductor is connected to filter out the ripples present in the current. Okay, and this armature voltage is applied to the combination of this 4 DC series motor. Okay, so why we have connected this 4 motor like in this arrangement? So there are 2 series DC motor connected in series and then connected in parallel. Okay, so in last class we have seen that if all the motors are connected in parallel, so we get, so if all the motors are connected in parallel, so the wheel slippage will be minimum. Okay, and addition will be good. Okay, if all the motors are connected in parallel, so tendency of the wheel slip will be lowest. But current burden will increase. So this will increase the current burden, or current rating will increase. Current rating will be high. Okay, and if all the motors are connected in series, so current requirement will be minimum. So current rating will be minimum in this case. Rating of current will be minimum, but wheel slip will be, tendency of wheel slip will be high. Okay, so coefficient of addition will be less in this case. Okay, so so there is a two case. If all the motors are connected in parallel, current rating would be high and wheel slip will be minimum. If you connect all the motors in series, so current rating will be minimum. So current required from the supply will be minimum, but there will be higher chance of wheel slippage. Okay, so coefficient of addition will be less. Okay, so thus we have to provide compromise between this contradictory requirement. So we have connected in this arrangement. Okay, so the current rating will be low and wheel slippage will be very less. Okay, so we have connected two motor in series and then connected in parallel. Okay, so that's why we have connected in this fashion. Okay. So transformer current rating will be minimum, okay, and tendency of wheel slip will be low, okay. So LD is divided into four sections and connected in series with each motor. If there is any fault, so this motor will have a high impedance in the circuit and the motor production will be simplified. Okay, and the braking in this case is provided by mechanical brake. Okay, so we normally use mechanical breakers to brake the motor. Okay, so this topology has got many disadvantages. Okay, so first we are using this on load tap changer. So this is has moving part and this whole part is immersed in oil. Okay, so this require uh, periodic maintenance. Okay, so this type of arrangement on load tap changer required frequent maintenance. Okay, so there are a large number of moving contacts. Tap changer requires frequent maintenance. The first disadvantage requires tap changers requires and they are very susceptible to frequent failures and fire hazards. Okay, and second, there is no smooth control in the speed. Okay, we have to change the taps. Okay, so there is a distinct control in speed control. So there will be current spikes when we change tap from one tap to another tap. Okay, so therefore there will be chance of wheel slip. Okay, and addition is poor. Chance of wheel slippage and addition is poor. Okay, as motor voltage is controlled in step, addition is poor. Okay, and there is a jerky way of control, and control is not very smooth. Okay, so addition is poor, and there will be chance of wheel slippage when we change the tab from one tab to another tab. Okay, so these are the disadvantage of this on-load tab changer traction and drive. Okay, so we can go for smooth control. Okay, so for smooth control, we basically use semiconductor controlled traction drive. Okay, so all these disadvantages can be mitigated by using these semi-control drives. So in semi-control drives, there will be a smooth control of the speed. Okay, so there will be no tab changers. So there will be no frequent. It will no. There will be no frequent requirement of this maintenance of these mechanical parts. Okay, so to avoid these disadvantages of this on-load transformer tap changer, we go with semi-controlled traction drives. So now we'll study 25 kV 50 Hertz traction using semiconductor converter control. So, sorry, this is traction mode. DC traction. Okay. So, what will we do? Again, this is 25 kV, 50 Hertz AC supply, overhead AC supply. So, again, we need step down transformer because motor rating is quite less. It cannot be up to 25 kV. So we need to need to step down the voltage. Okay. So here what we have half control bridge using SCRs. Okay. So we have two SCR. This is semi-controlled rectifier and two diodes. Okay, so this is fed to this secondary of the transformer, and here we have traction motors. So here we will use this filter LD and do DC series. Okay. So this is drive of shunting locomotives of 25 kV AC traction with Thyristor converter. Okay, so this is D1, D2, D1 and D2. So here there are no tab changes. Okay, no tab changes. So maintenance related to these tab changes is avoided by using this semi-controlled rectifiers. Okay, and there will be a seamless control over the speed of the DC series motor. Okay, and there is no distinct speed control. Okay, so there will be no wheel slipping and addition will be good. Okay, so this is step down transformer. It is controlled converter, and these are two traction motors. Okay. So we bring this AC supply to pantograph and this primary of the step down transformer, and the secondary is feeding the semi-controlled rectifier. Okay, two SCRs and two diodes are connected, and this LED is filter, which will filter out the ripples, and these are the DC series motor traction motors. Okay, you can use also because there is semi-controlled converter. We can use also the self separately excited DC motor also. Okay, so we require another converter, and we can connect the field of the motors. Okay, so you can use also this self separately excited DC motor also. Okay, so what are the advantages by using this type of power circuits? Okay, so first, smooth speed control. Okay, let's suppose this is GA. Okay, so So output of this rectifier depends on the triangle alpha. Okay. So by controlling this alpha, we can control the output voltage of this rectifier, and it is input to this combination of the traction circuit. Okay. So this is so we will see later what is the output of this converter and how it is depends on this alpha. Okay. So there is a smooth speed control of output voltage, and torque and speed control are smooth. So smooth speed and torque control. And smooth control of output voltage. Okay, so and it is highly efficient. It has got high efficiency. Okay, so this circuit don't have any resistance. There will be no losses. Okay, and we are using these semiconductor devices, so losses will be minimum. Okay, so it is very high efficient circuit. And third, there is no wind slippage, smooth control. So addition is better compared to tap changer. Okay. And it has low maintenance, low and easy maintenance. Okay. And you can connect PLCs, microprocessor to control the speed of this DC motor. Okay, and it has that is flexible control. So which makes enable to microcomputers, microprocessor, PLCs, and leading to optimal and efficient performance. Okay. So longer life. Next is longer life. Okay. So these are some advantages of using semiconductor controlled rectifier drives. Okay. So now we will see the output voltage and current taken from the supply. Okay, so we now will draw the characteristics of output voltage. Okay, so this is VA. It's from 0. So first we draw the supply voltage Vs. So this is Vs supply voltage. Okay. So it is like this. Okay, and it is a rectifier. You will get this type of. And suppose we triggered these thyristors at alpha. Okay, so the output voltage VA will be equal to Vs, and output voltage will be like this. So this is powering mode, powering reason. Okay, and this is alpha is symmetrical, B symmetrical, so this is pi. So this is pi plus alpha. So again we will start conducting like this. Okay, so this is what we output of this rectifier, and this is the input to this traction motors. Okay, so this is freewheeling period. Okay, so this period is from 0 to alpha. So there is it is freewheeling, and from alpha where we have given the firing pulse, so it will start conducting, and the output will follow Vs. Okay, so this is Vs, so it will follow Vs and up to pi. Okay, and then again this will be freewheeling period. Okay, from pi to pi plus alpha, and again we figure at pi plus alpha, so it starts conducting like this. Okay, so this is the output of the rectifier. Okay, and this region is powering region. Okay, powering region. So what do you mean by this freewheeling region? Okay, so the voltage is 0. So that means this motor are not connected to the supply. That means no current is flowing in this circuit, and this current is ID, and this current is SSI1, and this is IS. Okay, so the freewheeling path is provided by these diodes D1 and D2, and this inductor, and some inductor is present in the armature of this DC machine. Okay, so this freewheeling path is provided by these two diodes D1 D2, inductance LD and inductance of the armature. So now we will draw the waveform of IS, source current IS1. Okay. So this is 0, this is alpha, pi plus alpha, this is 2 pi. Okay. So from 0 to alpha it is freewheeling zone. Okay, so no current is flowing, so this will be equal to 0. Okay, and from alpha to pi, so this motor is connected to supply, so we will get quasi rectangular current like this, and the magnitude of this current will be equal to this DC current ID. So this is ID. Okay, and again from pi to pi plus alpha, this is freewheeling region. So again current will be equal to 0, and then from pi plus alpha to 2 pi, disconducting, but will get negative current like this. And obviously the value of this current will be minus I DC. Okay, so the current is not sinusoidal, it is rectangular in nature, rather quasi rectangular in nature, and it contains harmonics. Okay, so whenever we introduce these semi control rectifier or control rectifier, harmonics is injected in the power system. Okay, so the characteristics of this transistor is non-linear. So they will inject harmonics in the power system, and there will be some power quality issues. Okay, so these are the output VA voltage and IS current. Okay, so current taken by this converter. Okay, so disadvantage of this, the input current contain harmonics. Okay, so what is disadvantage of this circuit? So whenever we connect this semiconductor, so they will use some harmonics. So input current disadvantage. Input current contains harmonics. It is not sinusoidal in nature. Okay, so they are rectangle current, so they can draw harmonics from the supply. So if this is input current is not sinusoidal, harmonic current drawn from supply. Harmonic current drawn from supply. Second, this converter also draw reactive current from the supply. So this converter requires this reactive current. So we require reactive power. Okay. So there is a reactive power requirement. Okay. So which results in poor power factor. Results in poor power factor. So basically, this type of circuit has two disadvantages. First, it contains harmonics, and second, poor power factor. Okay. So this converter needs some reactive power. Thus, this results in poor power factor. Okay. So especially at low speed, at lower speed. So the transformer current, transformer draw harmonic current. Okay, transformer draw harmonic current. Okay, the power system get polluted and there are some power voltage issues there. So harmonic current and transformer get overheated and gets overheated due to this harmonic component. Okay, so if I is equal to fundamental component plus these are the harmonic component. Okay, so these are added to the fundamental component. So obviously current is increased. So I square R loss will increase. Okay, so therefore transformer get overheated. Okay, so these are some disadvantages of using this type of traction drive. Okay, so what we do, So we go. This is a single stage, a single phase, single stage converter. So we go for single phase two stage converter where we use two converters. Here we have used only one converter. So to avoid these disadvantages, we normally go for two stage converter. Okay. So before that, we will see how much reactive power requirement is there and what is the output voltage, equation of output voltage and fundamental component of current. Okay. So first V out is PA is average output voltage. Okay. So VA is average output voltage and which is equal to integration 2 pi V into upon pi sine omega t du. Okay, and it is integrated over 1 upon pi. Okay, so this is the voltage Vm upon pi, and here is conducting from alpha to pi. Okay, so on integrating this, we get, sorry, this is 1 upon pi root 2 V upon pi 1 plus cos alpha. We have this, we have derived this earlier, and we are studying this semiconductor rectifier. So VA is equal to root 2 V upon pi 1 plus cos alpha. Okay, and now fundamental component of input current. RMS value. So ID is equal to 1 upon root 2 RMS value 4 ID upon pi into cos alpha by 2. Okay. So this is fundamental component of input current. ID is equal to 1 upon root 2 for RMS value 4 ID upon pi cos alpha by 2. That means this current ID is lagging this source output voltage by alpha by 2. So this is displacement factor is this fundamental component of current contains harmonics. So draw start conducting from here. This is 0, this is VA minus 1 alpha pi plus alpha into pi omega t, correct conducted. This is 0, this is the, this is minus. Okay, so so when full analysis is done, so what we get, this current start conducting from, so this is alpha, so this is alpha by 2. So it will start conduct. So the current, zero current will start at alpha by 2. So this is fundamental component of current. Okay. So displacement factor or current is displayed by this voltage is cos alpha t. Okay, as this factor goes on increasing, power factor become lower and lower. Okay, so as cos alpha by 2 is increasing, so the power factor will be lower and current will gradually go down. Okay. So this is fundamental component of input current. So if displacement factor goes higher and higher, which results in power factor lower and lower. That's why power factor decreases and we get poor power factor. Okay. So converter draw a lagging factor from the supply. So converter draw a lagging current from the supply. Okay. So what we have derived, E naught is equal to 2 root 2 upon pi Vm1 plus cos alpha. Okay, V naught is equal to, this is 2. Okay. So what will be V maximum? V naught maximum will occur when cos alpha is equal to 1, or that is alpha is equal to 0. Okay. So root 2V on pi 1 plus 1. Okay. So this will be V naught maximum is equal to root 2 root 2 pi upon V, or this can be written as V naught maximum by 2 is equal to root 2 pi into V. So root 2 pi upon V can written as V max by 2. Okay, here. So V naught will be equal to V naught max divided by 2, 1 plus cos alpha. Okay, where V is RMS value of S. Where V is RMS value of V's. Okay, so that is V upon V naught maximum is equal to 1 plus cos alpha by 2. So take this ratio V naught by V naught maximum as V naught per unit. Okay, so this will be equal to 2 V naught per unit is equal to 1 plus cos alpha, or 2 V naught per unit is minus 1 is equal to cos. So this is the relationship between cos alpha and per unit output voltage. Taken as VA. So take this as equation number 1. So similarly, we can calculate the reactive power requirement by this converter. So reactive power Q is equal to V into I into sine phi. Okay. So this is voltage into current, and this is a sine of angle between V and I. Okay. So here, so Q will be equal to V, and value of I is 2 upon pi into ID into cos alpha by 2. We have written it earlier. And angle between V and I is sine alpha by 2, displacement factor. Okay. So angle between voltage V and current ID is displaced by alpha by 2. Okay. So this can be written as 2 root 2 pi into ID, and this is 2, so this is cos alpha by 2. Cos alpha by 2 sine alpha by 2. So this is 2 sine A, 2 into sine A, alpha by 2 cos alpha by 2. So this can be written as V into root 2 V by pi into ID sine alpha. Okay, so this is Q is equal to this root 2 VD. Okay, and we can write it as Q maximum. So Q maximum occurs when sine is 1. So this is 2 VD I into 1. So we can substitute here. So Q will be equal to Q max into sine alpha. Okay. So again, this can be written as Q upon Q max is equal to sine alpha. Okay. Again, take this Q by Q max as Q per unit. So Q per unit is equal to sine. And let's take this equation number 2. So this is equation number 1. So squaring both this equation and adding equation number 1 and 2, we get. So this is 2V out per unit minus 1 whole square plus Q square per unit is equal to cos square plus sin square, which is equal to 1. Okay. So this is the relationship between per unit output voltage and per unit reactive power. So this is equation 3. So using this equation 3, we can draw a graph between V out per unit and reactive power per unit reactive power. Okay, so this is very important formula. Okay. So when let's take V out per unit is equal to 0, initial value as 0. Okay, substitute here. So this will be equation number 3. So this will be 0, 2 into 0 minus 1 whole square plus P per unit whole square is equal to 1. Okay, so this will be 0, 1 square is 1, 1 plus Q per unit is equal to 1. So Q per unit is equal to 0. Okay, so when V per unit is equal to 0, so Q per unit is also 0. Next, when let's take V out per unit as 2.5. Okay, this will be 2 into 0.5 minus 1 whole square plus P per unit whole square is equal to 1. So this will be 1. 1 minus 1 is 0. So 0 plus per unit square is equal to 1, or Q per unit is equal to 1. So when output voltage per unit voltage is half, so we get maximum per unit voltage, which is equal to Q max. Okay, so per unit voltage can be maximum, which is equal to 1. And we take another condition when V per unit is equal to 1. Okay, so V per unit can be range from 0 to 1. Okay, so 1, 2 into 1 minus 1 whole square plus P per unit whole square is equal to 1. So 2 minus 1 is 1, 1 whole. So this will be P per unit equal to 1. So P per is equal to 0. Okay, so when maximum voltage, output voltage is required, so the reactive power is 0. Okay, so using this we can plot a curve between V out per unit and Q per unit. Okay, so at when V naught is 0, so Q naught is 0, and when at half it is maximum, and again at 1 it is 0. So this will be the curve. Okay. This is like this. Okay. So at point 5, this will be Q maximum. It is 1. Okay. Equal to 1. So here alpha is equal to 180, and when for Q max alpha is equal to 90, and here alpha is 0. Okay, so this is the plot between V per unit and Q per unit. So reactive power is a function of output voltage. Okay, so reactive power is function of output voltage. So when we increase the output voltage, so the reactive power also increases like this, and it becomes maximum at V naught per unit is equal to 0.5, and then if you increase voltage, the reactive power decreases gradually, and this plot is drawn in accordance with this equation. Okay, so this equation is very important. So we have substituted various value of V naught, and we got this curve. Okay, so when V naught is 0.5, maximum reactive power, and converter requires lagging power factor from the supply as IS lag Vs by cos alpha by 2. Okay. So we have to compensate this reactive power. Okay. So there should be a compensation to compensate this reactive power. So we normally go with single phase 2 stage. Okay. So we are discussing right now. We are discussing single stage, single phase, single stage converter. Okay. So to avoid this disadvantage, so single phase 2 stage converter is used. Okay. So in next class we will discuss single phase 2 stage converter. Okay. So any doubt in today's class? Okay, then we will see single phase two stage converter in next class. Okay, thank you class.